Okay, this presentation tonight is about working the International Space Station. We'll look at the hardware, the methods, and some of the hints that I found in working satellites, probably for the past 10 years or so, that may be of some benefit to you. The ISS, or International Space Station, has been continuously occupied since November 2nd, 2000. Staffed primarily by American and Russian personnel, but crew have included astronauts from 19 other countries, including 8 Canadians. A joint project, the primary mission is as a microgravity and space environment research laboratory. Earth orbit satellites, or known as LEOs, which include the ISS, circle the Earth at approximately 2,000 kilometers, height or less. The ISS average altitude of 400 kilometers, and its size, 110 meters by 100 meters, make it the largest artificial object in space and the largest satellite in low Earth orbit. It's regularly visible to the naked eye, particularly if you're viewing it at night, under a clear sky and the ISS happens to be in sunlight. At this height, the ISS orbits every 93 minutes, plus or minus a few seconds, completing 15.5 orbits per day. Its footprint, the area that it covers on Earth at one time, may result in radio distances of 400 to 2,500 kilometers. And that's not bad if you're using a handheld for an FM contact. Previously, the voice contacts with the ISS were limited to astronaut contacts. You had to be really lucky or be participating in a scheduled event to succeed. SARC did make direct contact with astronaut Reed Wiseman, Kilo Foxtrot 5 Lima Kilo Tango, using the ISS call of November 1 Sierra Sierra. And that was during field day of 2014. But as of recently, there's a repeater aboard the station. The repeater need not be staffed by an astronaut and operates much like a really high repeater here on Earth. The advantage, of course, is that there are no obstructions to interfere with your input or the ISS signal. This animation shows the position of various satellites as they orbit the Earth. Geostationary satellites hold one position over a particular point in the globe and rotate with the Earth. Types of satellites like this might be used for radio and television. That's compared to transitioning satellites, which continually circle the globe, and because the Earth turns, they cover a slightly different area on each pass. They orbit much closer to the Earth than the geostationary orbits. As satellites are further out, their speed decreases, and some orbits are egg-shaped. These satellites can have a huge footprint at their highest point that cover almost half the globe, and there are a couple of different amateur radio satellites that have egg-shaped orbits and on which you can cover tremendous distances. So working the International Space Station, depending on the orbit, the ISS may approach at different angles. It may be a south to north pass, known as an ascending pass, or a north to south pass, a descending pass, so you have to determine whether the pass is towards the east or the west of your location. Although it does occur, and is the best, it's rarely directly overhead, and we tend to get 2 consecutive passes, one to the east and one to the west, timed about 90 minutes apart.
Whiskey 7 Alpha India November, loud and clear. clear for the station. USL.
Victor Echo 7, Sierra Alpha Romeo.
Victor Echo 7, Sierra Alpha Romeo, clear.
Woo! We made it! We made it!
And as usual on this day, I hear a lot of folks calling. Keep trying. I'm hearing you. I'm trying to get back to as many as I can.
Obviously, the best and longest passes have the highest elevation, passing directly overhead. I found that passes over 60 degrees above the horizon should work with a handheld transceiver, and lower passes with a directional antenna. Being located as we are in a mountainous area, we often have no choice when passes are below 20 degrees. Mountains tend to get in the way around here on very low passes. This chart shows a typical one-week schedule. The center column is maximum elevation. That is the key element for a beginner. Note the pass on Sunday in the middle of this chart. It's 83 degrees and it starts at 5:02 p.m. lasting 6 minutes. That's a great pass for beginners. The passes at 20 degrees and less would not likely be successful for basic equipment, and they're very short. But how do you find a chart such as this? Fortunately, there are many choices for free and low-cost apps for Windows, Mac, Linux, and iOS and Android portable devices. I tend to use my iPad to plot the pass, and my app of choice is called HamSat, although I have 3 other tracking apps that I have installed for specific applications. I use my iPad because it's less bulky than my computer and it's very portable. I use my iPhone as an audio recording device, but more on that later. If I were using a motorized device for pointing my antenna, I'd be using a computer, as computer tracking software requires certain drivers. On the slide, you'll see a number of suggestions for different apps, app names. Don't bother making notes necessarily of these. The entire list will be in the next communicator, and I'll also make this slide deck available online. To work the ISS repeater, you can use what you use to access any other VHF or UHF repeater, your stock equipment. If you get a bit fancier, your results will be better as you can work lower passes with more airtime. But first you'll need to look up the time of the pass and the direction using the web app, an app or computer software. And then you'll need at least a receiver capable of tuning to 437.800 megahertz in the UHF band. If you're going to transmit, you'll need a transmitter capable of 145.990 megahertz in the VHF 2-meter band, and you have to have the ability to transmit a 67 hertz subaudible CT CSS tone on transmit. This tone acts like a key and opens up the ISS transmitter. I personally find that a handheld mic is preferable to trying to balance a transceiver. And if you're in a noisy environment, using earbuds or a headset is preferable to cut down on extraneous noise. A recording device is optional, but if you get a good run, you don't want to be stopping to note down call signs and coordinates. I use the audio recording app on my iPhone. You don't need high power. Use no more than 10 watts, and I find 10 watts is generally plenty of power. Remember, there's nothing in the way. It's just you and the ISS with nothing in between you. Remember as well the Doppler effect. The Doppler effect, or known as Doppler shift, is the change in frequency of a wave in relation to an observer who is moving relative to the wave source. It's named after the Austrian physicist Christian Doppler, who described the phenomenon in 1842. A common example of Doppler shift is the change of pitch heard when a vehicle sounding a siren approaches and recedes from an observer. Compared to the emitted frequency, the received frequency is higher during the approach, identical at the instant of passing, and lower during recession. The reason for the Doppler effect is that when the source of the wave is moving towards the observer, each successive wave crest is emitted from a position closer to the observer than the crest from the previous wave. Therefore, each wave takes slightly less time to reach the observer than the previous wave. Hence, the time between the arrival of successive wave crests at the observer is reduced, resulting in an increase in frequency. While they're traveling, the distance between successive wave fronts is reduced so the waves bunch together. Conversely, if the source of the waves is moving away from the observer, each wave is emitted from a position farther from the observer than the previous wave, so the arrival time between successive waves is increased, reducing the frequency. The distance between successive wave fronts is then increased so the waves spread out. Now this sounds like a lot of technical mumbo jumbo, but if you're just trying this for fun and you're able to work a high path, you should have several minutes of good access even without worrying about Doppler frequency shift. Although the satellite might sound distorted lower in the sky when it's rising and again when it's descending, or you may not hear it at all at the extreme ends of the pass. But for the majority of it, at the peak, it should be just fine without worrying about Doppler shift. So if you're going to program for Doppler shift, this is the recommended method. Typically, each satellite will take 5 memory slots, which is not a problem on most modern radios. In the case of the International Space Station, you have an uplink frequency of 145.99 megahertz with a 67 hertz tone, and a downlink of 437.800 megahertz FM. And compensating for the Doppler shift, you have AOS, which is the acquisition of signal in the first memory slots. With that, you increase the frequency by 10 kilohertz. When the satellite is rising in the second memory slot, you increase it by 5 kilohertz for the downlink frequency. At the top of the pass, TCA, there is no Doppler offset. Descending would be memory slot floor with a minus 5 kilohertz shift in downlink frequency. And at loss of signal, or just at the termination of the pass, it'll be minus 10 kilohertz. So as you can see from the table, you typically shift the receive frequency by plus or minus 5 kilohertz steps from the base frequency and program these into your memory channels. So let's look at the hardware that you're going to require. I've worked a number of low Earth orbit satellites, and some need much greater effort and better equipment than others. For the ISS repeater, depending on the pass, I've succeeded using any of the ones that are shown on your screen. Some are usable for receive only, for example, a receiver, a scanner, or an SDR dongle, and you don't need an amateur license if you're just receiving, of course. What's better is a dual band handheld with a stock rubber ducky or better antenna. A simple wire counterpoise will enhance your efforts quite a bit because that makes up the other half of your dipole antenna. The best is a dual band handheld with a directional antenna or 2 transceivers, one for VHF and one for UHF, which tends to get a bit awkward. But certainly a directional antenna, even a homemade one, will outperform your rubber duck on your handheld radio. Ideal is a dual band mobile with directional antenna. It's easiest to program. There's less fiddling with knobs as the satellite passes. And with a directional antenna, of course, you can work much more of the pass and much lower passes. Well, I'll repeat again that you can work the International Space Station quite easily with a handheld radio and a stock antenna. I have made several successful contacts on passes with my Baofeng UV5 and the stock antenna. A slightly longer aftermarket antenna is better, and of course your antenna is equally as important as your radio if you're trying to make long distance contact. But certainly in order of preference, a stock rubber duck antenna would be at the bottom of the scale. It does work better if you add a counterpoise pigtail like that is shown in the bottom picture on the slide. That's simply a length of wire cut to the frequency that you're using, wrapped around the base of the antenna, so it's on the ground side of the antenna, or attached to a screw on the case of your radio. Basically that makes up the other half of a dipole antenna. At less than 45 degrees elevation for a satellite pass, a fixed quarter wave or vertical mag-mount antenna, for example on top of your vehicle, will work quite well. Once it gets beyond 45 degrees elevation, of course, the radiation pattern of that antenna is less successful, although it'll probably still work maybe up to as much as 60 degrees. A tape measure Yagi. The internet is full of do-it-yourself plans, and we featured it in the previous communicator newsletters. Tape measure Yagis, as shown in the picture there on the slide, the top picture, are quite easy to make. They're very inexpensive to make, and of course you get the benefit of having a directional antenna that has some gain and produces a much stronger signal both on transmit and on receive. Then of course there are commercial or do-it-yourself antennas like the Arrow or the Elk. The Arrow antenna is shown in the middle picture there. It is a dual band antenna, and it works very, very well for even the most difficult to work satellites. There is a file on the internet on Whiskey Alpha 5 Victor Juliet Bravo site called Cheap Antennas for LEOs, and it's full of antenna ideas of inexpensive antennas that you can make to work the satellites. Of the software app that I use, this one here is Hamsat for iOS, who's on my iPad. But there are so many packages out there that it's impossible to document all of them. But the principles are basically the same. All the software and apps that I have used update something called a two-line element file, TLE file, from the internet on a regular basis. So before you start, you should make sure that file is up to date. Sometimes the software will do it automatically when you start it, and sometimes you have to push on a button in order to update it. If you don't, then you might find your satellite timings, the past timings might be off by either several seconds or perhaps a minute or two. And without going into the complex math involved, the TLE file is basically a data set listing orbital elements of an Earth orbiting object for a given point in time. And using a mathematical formula, it states the position of velocity at any point in the past or future so that it can be estimated with accuracy. Once your TLE file is downloaded and you've entered your location, you should be set to go. The first screen I look at shows the footprint of the satellites I usually work. That's the one on the left. Select the satellite you wish to work, for example the ISS, and on an iPad I can just tap it. And the software should then provide you with a list of upcoming passes. If you're new to this, pick a nice high pass. It'll be easier to work and it will last longer. The example on the right shows the next screen with circles 15 degrees elevation apart. The outer ring is 0 degrees, the horizon, and the center is 90 degrees, which is straight up. This example shows a pass with a maximum elevation of 60 degrees. The pass starts in the blue, so from the west, and arcs across the sky toward the north at the highest elevation, then descending to east-northeast where it dips out of range. Here are some of the terms you may encounter in your software. The word ARM is sending a CTCSS, or a subaudible tone, with your transmitted signal to open up, to unkey to key up the satellite's transmitter. AOS is acquisition of signal, the time the satellite comes into view and you may be able to contact it. I rarely work satellites below 20 degrees as a result of our local terrain, and besides, a 20-degree pass would only last a few minutes. RIS, or rise, is rising. The satellite is rising above the horizon, so you have to adjust your Doppler to compensate. TCA is time of closest approach. This is the time when the satellite is closest to the observer and the Doppler shift is 0. This usually corresponds to the time that the satellite reaches the maximum elevation above the horizon. DES, the satellite is descending towards the horizon. Adjust your Doppler again. LOS is loss of signal. The fun has ended for this pass as the satellite has passed below the horizon. LON and LAT is longitude and latitude of the satellite. ALT is the altitude of the satellite. VEL, velocity, the speed of the satellite. AZ is azimuth, the variation from north, 0 degrees, of the satellite. EL is elevation in degrees. In this example, it is minus because the satellite is below the horizon. Range, how far away it is. And the rate is the speed at which the satellite travels relative to your location. So these values, when you're looking at the software, will constantly change as the satellite approaches or passes by. And in this particular software, as soon as the satellite comes into view, a dot appears on that curved arc, showing where the satellite is in the sky at any given time. This is astronaut Peggy Whitson, and she's holding one of the amateur radio antennas prior to installation on the space station. The antenna is one of a series of 4 which are clamped on the handrails around the Russian service module. And there's also a quarter wave vertical antenna on the space station. The inset picture on the lower right actually shows the ISS transceiver, which is a Kenwood D710GA. And of course, they have to modify it slightly with proper shielding and to make sure there's no sparks or any other issues while it's on use on the space station. But it's basically the same transceiver that you might buy locally at the amateur radio store. So the ISS repeater is similar to working a terrestrial repeater. You'll have to enter at least these frequencies into your transceiver if you're going to have a two-way conversation. A downlink or receive frequency of 437.8 megahertz FM. An uplink transmit frequency of 145.99 megahertz with a 67 hertz CT/CSS tone. You can use additional frequencies if you're compensating for a Doppler shift as described earlier. It's a big offset between receive and transmit, minus 291.81 megahertz, but some transceivers can be programmed for it. On my Baofeng UV5R, I use 2 channels, one for receive and one for transmit, and I can monitor the receive frequency on one set while I transmit on the other. Some use 2 separate radios, one for transmit, one for receive. I find that I don't have enough fingers to manage 2 radios at once, but if that works for you, then that's certainly a good solution. Remember though, low power is adequate. There's no need to blast out 50 watts. In most cases, 5 watts will do. Other than the foregoing, the operation is just as for a terrestrial repeater. If you're operating with a handheld and rubber ducky, you'll have to perform some wrist maneuvers as the satellite rises, passes, and descends. When it's overhead, rotate your handheld so that the antenna is oriented more horizontal to send out a better signal in the vertical direction. And toward the horizons, bring the antenna more upright to a vertical position. So next we'll look at Maidenhead Coordinates. And what is a Maidenhead Coordinate, you may ask? Typically use something called the Maidenhead Locator System, also used known as a Q2H locator and IARU locator. It's a geographic coordination system used by amateur radio operators to succinctly describe their particular location. Its purpose is to be concise, accurate, and robust in the face of interference and adverse satellite or transmission conditions. The Maidenhead Locator System can be used to describe locations anywhere in the world. In each pair, the first character encodes longitude and the second character encodes latitude, dividing the globe into 18 zones of longitude of 20 degrees each and 18 zones of latitude of 10 degrees each. Greater Vancouver is at the very northeast corner of Charlie November. For satellite work, we use only the first 4 characters, although using the maximum set of coordinates, you might have as many as 8 digits. There are maps readily available if you search for Maidenhead Locator map on the internet, and you can have a closer look, but this example here shows where we are located in Charlie November 89. Typically on a satellite contact, that's exactly what you would use is your locator, Charlie November 89, and whoever you're speaking to will no doubt provide their locator. There is a pastime of trying to collect as many locators as possible, and certainly with passes of high satellites, you'll be able to get most of the locators within 3,000 or 4,000 miles. Well, one of the things we ran into with our students from our basic classes is being mic shy. What do I say? How do I do this? Well, don't be mic shy. Be prepared for busy airtime during a daylight space station pass, particularly if it's a high pass. The weather is nice and it's during the daytime. Lots of people are out there right now because it's a relatively new thing, and people are anxious to try and collect some of those Maidenhead locator squares. Most hams sleep at night, but a contact can be made for us diehard fools who are up at all hours. Typically there's way less traffic at night, but there are other hams that are equally foolish and stay home, on the repeater at night as well. Typically I wait so as not to interfere with another station, and if the air is clear I say Victor Echo 7 Tango India, Charlie November 89. This gives my call and locator, and pretty soon you'll generally get somebody coming on the air answering your call. Just wait for a confirmation, which will be the other party's call sign and locator. If there's no answer, call again. And if you hear someone else, answer with your call and your locator. If it's not busy, which does happen occasionally, there's time for a chat. That rarely happens on the ISS repeater. It's so new, and there, like I said, many hams still anxious to use it. Recording of a pass.
AKV AB10C. Hello, John. It's Fred, New Hampshire.
AB10C, hey Fred, sounding good, and Fox Mike 05, Cary, North Carolina, KG4AKV.
Thanks and stay safe. All the best.
Guys, with the handhelds, with this bird being only 422 kilometers up, it's going to be real easy to get in.
A3HTO.
I'm sorry, I doubled with someone. Who was the other station?
AA3HTO, KO4MA.
Now, one of the astronauts would just get on is my day. KO4MA and S3L, 59 Foxtrot 20.
Although this article focuses on the simple part of working the ISS repeater, you may want to venture a little bit deeper. Although it's not constantly active, the Russian crew members are frequently active sending amateur slow scan TV, known as SSTV. Each image takes about 3 minutes to receive, and you can access it on 145.800 megahertz FM, simplex receive only, but it's very simple. You simply monitor during a pass that lasts at least 3 minutes and hold your receiver to a phone or computer that has the app or software program installed. Line by line, the image will appear. You can also make an audio recording and play it back later, as long as you do not use any audio compression methods like MP3 or AAC. Again, there's lots of free software for portable devices, Windows, Mac, and Linux, but the most common one for SSTV is probably a package called MMSSTV. If you have access to a terminal node controller or TNC or a transceiver with APRS, Packet radio via the ISS may be for you. It too is easy to work and is always active at 145.825 MHz simplex. And if you go to the site www.eris.net, that's Alpha Romeo India Sierra Sierra.net, there's lots of explanation to get you started. Here is what the SSTV picture sounds like coming in. And again, note that he's using a Baofeng UV5R just with a stock antenna. Now, the question that I get asked most often when I'm doing satellite work is, can I talk to an astronaut? Well, yes, you can if you're lucky. All astronauts have a ham license. It's one of their backup communication systems, and as you've heard before, if all else fails. It's possible to contact the ISS crew members. Depending on the schedule and level of interest, they may or may not spend their spare time on the station's amateur radios. Some past astronauts have been very active, some not so much. Crews work on a UTC schedule, so usually 0600 Zulu to 2200 Zulu, which is 10 p.m. to 2 p.m. Pacific time. Then they say that their lunchtime, 4 a.m. Pacific time, is a really good time to try. But of course, I'm not always up at that hour. And there are other low Earth orbit satellites that you may want to try to work. And although some of you may not care to try, here's a list of the other LEO satellites in order of difficulty that can be worked with a bit more patience. Further information on these and more can be found on Clint Bradford Kilo 6 Lima Charlie Sierra's site. It's very good for beginners on working satellites, and that's www.work-sat.com. Patrick Stoddard, Whiskey Delta 9 Echo Whiskey Kilo, who also has a Canadian call sign of Victor Echo 7 Echo Whiskey Kilo and has spent some time locally. Also has an informative site. I've talked to Patrick several times, and he's very knowledgeable and active. And he's at www.whiskeydelta9echowhiskeykilo.net. And finally, the ISS Repeater is almost always available, but occasionally it's turned off. You can check the current status at the amsat.org/status website and look for the ISS-FM entry, and that'll tell you if it's down for maintenance or because of some other reason. So that is the presentation. Are there any questions?